This is a different propulsion technology. It's the other side of the scale. I'm François Martel with eSpace, and this technology, the ion electrospray thruster technology, is developed at the Space Propulsion Laboratory in the aerospace department at MIT by Professor Paolo Zano, and Natalia Brickner is one of Paolo's students who is focusing on transferring the technology from laboratory to industrial production. It's an evolving technology. We have gotten funding from different parts of the government, including NASA and DoD, several NASA centers, and including small business innovative research. So the electrospray thrusters, the principle, oh, I think I'm going too fast here. That's the laser, okay. They are using salts that have the property of being liquid at room temperature, and with surface tension properties such that they, through capillarity, can migrate through porous materials. The porous materials are developed into substrates supporting microfabricated emitters, and on top of the emitters there is an electrode which is placed very close to the emitters, such that if you apply a voltage between the electrode and the emitters, you get a very, very high field, electric field, and that extracts the ions from the emitters through openings in the electrode. So if you have a positive difference, the negative ions will be ejected. If you have a negative difference, the positive ions will be ejected. So you can alternate between positive and negative ions and keep things about neutral. Now, this is a picture of a grid with 500 holes, basically, for the 500 emitters for the current thrusters. In the future, they may have even more emitters. It's about a square centimeter size, and this is a full thruster. So you can see it's very small. And the thrusters are usually paired so that you have one side emitting the positive ions while the other side is emitting the negative ions, and you alternate, so you keep a neutral beam, keep everything neutral, and the currents are the same on both sides. So the thrusters are very small, low mass, low volume, and they provide competitive thrusts for space propulsion and very good efficiency. The ISP is very high, so the volume of propellant required is not is small, and they have no moving parts, no valves. All the propellant motion is through capillarity, and they are also, another aspect of them, that modular, which means that you can develop them into arrays of any size. So you can go from very micro propulsion to large array for large propulsion. So that's one, it's part of the application. So there's a wide range of application, enormous dynamic range there. This is a picture of an emitter array. So you can see the microscopic picture of the emitter, and the liquid salt through capillarity moves to the top of the emitter, and when the field is applied, it forms stellar cones, and the ions are ejected at very high velocities, so high ISPs. This is a typical curve. It's not those thrusters are evolving, so don't take this as the current performance, but shows that curve is there to show that when you apply a voltage to the thruster, at some point there's a threshold at which they start emitting. It's very sharp, and then there's a very sharp dependence to voltage. You can increase the currents, in this case 200 microamps, but it can go much higher. And when you change the opposite voltage, of course, you have the opposite curve for the other type of ions. The specific impulse is typically between 1500 and 3000. Thrust density 0.1 to 0.2 Newton square meter for this type of thrusters, but the technology is evolving, so the thrusters performance is increasing in time. And by controlling the Electrospray grid potential and the pulse duration, you can modulate the pulse to, as I said, a wide dynamic range. So this is a picture of assemblies built with the thrusters. You can see in this very recent picture, here you have a whole assembly where you have 4 pairs, and there's room for actually an additional 4 pairs, so you could have 16 modules on this one. And the idea in this small business innovative research development was to have propulsion, and you could put the pairs sideways to get also torque in all axes. So in a configuration like this, you can have, let's say, roll with these cross-strapped detectors, and then those detectors could provide pitch or yaw in combination with thrusting or pure thrusting if you run them at the same time. So this assembly includes a high voltage board and high voltage switches, integrates the thrusters, and it works from 5 to 8 volts with a SPI interface, RS-232 interface, and it's something designed for flight on a CubeSat, and it's going to fly pretty soon. So now applications to, because of the very high ISP, we can build systems with the small thrusters and a small amount of propellants to achieve quite a bit of delta V, especially for CubeSats. So in this couple of calculations indicating that starting from a 600 kilometers low Earth orbit, you could with 320 grams take a 3 kilogram 3U CubeSat to escape. Or if you start from a geosynchronous altitude with 127 grams of propellant, you can get to escape also. So for lunar missions or interplanetary missions, you can have a system that fits in a CubeSat and provides a very significant propulsion. One of the MIT students, Caleb Whitlock, did some estimates of what it would take to go from a geosynchronous orbit to near-Earth orbit and to make a rendezvous with a near-Earth orbit object. And he picked up, as an example, a 1991 VG. And in his was sort of kind of a brute force calculation. We didn't optimize the trajectories too well, and he estimates that he needed 3,500 kilometers per second delta V. And so with a 40-watt 6U spacecraft, that would require about 1.2 to 1 kilo of propellant. With 80 watts, you basically shorten the time, and of course, if you use some other techniques, you can actually reduce those numbers. So the idea was, what does it take to get something that gives us ample margin to do such a mission? And this is a sketch of what a 6U sort of envelope, and it's kind of comfortable for a 6U mission to get 3.5 kilometers per second delta V. So in that sketch, you can see the array. The array of thrusters covering two faces. They can be grouped in quadrants, so you can actually get attitude control at the same time you get propulsion, so you can orient a spacecraft also. And there is an excess of electronics card here. I think one of the boards there would be enough, and 2 but not 3. So and that tank is kind of deep for even for that size. So that it gives you an overall envelope for a 6U mission to get 3.5 kilometers delta V with that technology. Another example, Caleb worked on a lunar impactor, and in his example with 4.5 kilograms of wet mass and 25 watts, he required about 318 grams of propellants to get to the moon either in the lunar orbit or any grazing impacts for some science applications. Another application, of course, of interest to me, that's how I got involved in electrospray propulsion, is the idea of and Bob Bagnall discussed it earlier. It's developing a RF pulse array in space, and the idea is to use nanosats with their own propulsion to create a sparse array, and each nanosat becomes an element in the antenna, and then talks to either they are a multiplex system between them, or they talk to a mothership, which could be a small mini-sat, and the information then is sent to the Earth to provide basically imaging in the RF range, which has never been done up to now. So that's one of the applications, and it's actually very interesting because you could conceive of a sphere of maybe 1 kilometer wide of CubeSats that are, let's say, for example, on Lagrange points and just hovering around each other, and the delta V's comments are very low. The propulsion system can last for a very long time and keep that observatory in place for a very long time to image the whole celestial sphere. So that's an application of interest. And I guess that's where this presentation ends.
Thank you.
Okay, well, that's, at this point I'm done, yeah.
Thank you.
Yeah.
Walter has a question.
When do you expect to put this in orbit on any mission?
There's a plan that I can't really discuss in too much detail, but there's a plan for launch in the spring.
Okay.
Yeah.
And so you've verified performance on the ground?
Right. The thrusters are operating in vacuum on the ground, and there is actually a NASA project now called MEP for the propulsion systems. Mike Lozano is one of the PIs on that project, and the goal there is to operate them for 200 hours. We have operated thrusters at 70 hours in the vacuum tank and without seeing any degradation of the tips.
Okay.
So,
are there any, one of the concerns that we have making small spacecraft and pumping in, say, 80 watts, is that we'll get too hot somewhere. Are there substantial heating issues that you solved or seen?
Yes. The current board that you saw were in the 3-5 watts range for small CubeSats. The 40-80 watt is when you want to get a 6U to an asteroid and you want serious propulsion with a large array. The thrusters themselves do not really heat up. Actually, one of the issues is to keep them warm enough. So in the current CubeSat experiments that we're working on, actually the concern was that we needed to place the heater to make sure that the thrusters were warm enough to start operation. Because those cells, if you get too low in temperature, could actually become solid, and then you.
But surely you have efficiencies, and surely.
Yes.
Okay.
Right. So then you need where the heat is dissipated is in the conversion from the bus to the high voltages.
Okay. Ballpark.
Yeah.
I'm sorry to dominate all the questions,
Right.
but ballpark. If I pump in 100 watts into the system for propulsion, how much of that power can I expect to be heat that I have to subsequently dissipate?
Well, if you pump 100 watts, you're in a better situation because you have a larger amount of power, and it's easier to make a high efficiency converter from there. So so the question is how high efficiency can you achieve from your bus to the several thousand volts used for the thrusters? And depending on the voltage of the bus and the way you build your converter, that's the efficiency. So we have in test push conversion to 91%.
So it's
on the electrical conversion from low voltage to high voltage.
So it is reasonable as a thumbnail
right.
for us to expect that for every 100 watts we put in, we have about 9 watts of heat?
Yes, there'll be some other dissipation. So, right, I mean, the efficiency numbers that we have seen in testing and with our small things were from 70% to 90%. Okay, so you're somewhere in that range.
Right. Thank you.
Yeah.
I have a question. So have you looked at low energy trajectories that would substantially reduce delta V? And I mean, as you were using 3.5 kilometers per second to get to an asteroid, I think it looked like you were using just a raising apoapsis.
Right. Yes. It's as I say, it's sort of a brute force calculation was done relatively quickly, and Caleb said you could optimize largely, but we want to see what envelope we needed and how it fit.
And one of the reasons I asked that is because I wondered what the trade space would be like, for example, if you had, I don't know how much volume you were using for that system, but if, let's say, you had somewhere around 1 U for propulsion and 40 watts, what would be the result of that?
Okay, just maybe go back to the slide. Oh, are we? Can we enlarge that that slide, maybe?
Let's go.
So you say what? You can see that the volume here is about 1 liter. Okay, one cube.
Oh, okay. It's about 1 U. Okay.
Right. That's the volume of propellant, and to that you add some electronic scales and the thrusters themselves, which is not very much.
And what if you? I mean, what would be the impact of? Oh, and I see you do have 40 watts up there.
So if you look at 40 watts, and how much delta V you wanted?
Well, I'm just thinking of this in terms of what we would need to get to the moon.
To get to the moon. All right.
You know, we're looking at something on the order of probably 1.5 kilometers per second with a substantially long trip because we're using, you know, maneuver, basically some burns on these low energy trajectories.
So 1.5 kilometers per second, and a 6U. So let's go back to the picture here. This was calculated for 3.5 kilometers per second. So you take half of it basically.
Right.
So you should cut. Okay, most of the volume is taken by the reservoir of the tanks. So you just cut that in half. So here what you have is you had basically 2 U's.
Looks like 2 U's, yeah.
So yes, so you take a bit more than half, maybe. So yeah.
Okay, well, that's reasonable. Thank you.
Thanks. This is Russell Cox, and now I have my select investor hat on. So tomorrow we're going to talk about startups. So talk a little bit about you're ready to start selling product. Where are you in that, and how are you envisioning your company?
Right. So at this point, there's a team at MIT composed of Paolo Lozano's students, and it's called Axion, and it's just a nascent little company, but they are tooling to start manufacturing the thrusters, going from the lab to production. So right now, they are every thruster is all the thrusters are built in the lab. They are built in on wafers, and there are some, but it's still a lot of hands-on manufacturing, and so it's time and student time, and the yield is good, but it takes time to build those thrusters. They are there. And the idea is to automatize that and freeze the design at some level, because design also, it's R&D, it's serious R&D, and the design is evolving. I mean, I expect those thrusters to become, to get higher density. Also, you can vary the propellant and get also higher thrusts from those. So the expectation is they will improve, but at some point the team will define a standard design and start producing them for some applications. And one of the drivers also is to make them completely modular, including the PPUs, including the power processing unit.
Any hints or estimation of cost?
Excuse me?
Cost?
Right now, I say it's R&D, so it's people's time. Once you get into industrial manufacturing, costs are going to drop dramatically.
Yeah, but we're talking thousands, tens of thousands, hundreds of thousands.
By now, it's people's time. So if you spend weeks and months, you can do the math. I mean, if you use students and they don't cost you too much money, it could be cheap, but it's still okay.
Okay, thank you.
This is Jeff Harvey. I was wondering, what is the volume? Does that volume you're showing there include the voltage converter volume, or is that just the thruster
Yes,
volume?
so that sketch was done by Caleb, and he took our 3-board design and just extended it on 2 faces. So you see, basically, it's like the top here is like the small pita board system you saw before, and the bottom is like the 3 boards behind. We don't need those 3 boards, so you could drop one with no problem, and actually, depending on how complex you want to do the switching and how many thrusters you want to control independently, I believe actually one electronics board is sufficient. So you're talking about a 10 by 20 centimeters board behind the tanks and the thrusters to get it out.
And that board is the board that goes from spacecraft voltage to a couple thousand
correct,
volts.
yes,
Okay.
yeah.
And that's the one that was running at 70 to 90% efficiency.
Right, yes,
Okay.
yes.
So it's
And it really depends on where you start from, because you have an FPGA and you have electronics controlling the whole thing, and then you have the actual conversion. So if you start from low voltage for a low power system, of course your overhead is higher and efficiency is lower. If you work with a high power, then the conversion becomes the dominant factor, and in which case you can actually raise the efficiency. Yeah.
Thank you.
On the asteroid mission, is that a flyby or a rendezvous mission?
I believe it's a rendezvous mission. Yeah.
With your
Is that right?
yes, with your that synthetic RF experiment that you're planning to do, if it's not violating any proprietary information, how many satellites were you interested in using for that?
Well, this idea is based on a concept called CIRA, and Bob could talk about it because he was one of the leaders in that project. And the initial idea was to use a constellation like this to look at, to image the sun in the RF, and the estimate was 12 to 16 satellites at the time were good enough. And at the time of CIRA, the satellites were mini-sats, so it was very onerous. But the idea is to, as Bob described in his paper, to use nanosats and CubeSats to provide most of the elements in the array. So.
Just a couple quick questions. I may not have caught how much the entire system weighs. You've got a kilogram of propellant, but the entire system weighs how much?
Oh, yeah, most of the weight is in the propellant. The thrusters, I don't have a number. You saw them in here. They are very small and very light, and the boards themselves are like 40 grams each or something. So let's say 100 grams of board, and the rest would be propellant.
And then, just to check my math, then you have something like 2 millinewtons of thrust from the 6U version. Is that correct? I was getting from your thrust numbers per square meter.
Right. Okay. Yeah. Yes. Good point. If you look at Caleb's numbers, he's using 78.6 micronewton per pair, so it's about 40 micronewton per module. And the slide on top was giving something like 20 micronewton. This because the thrusters are evolving, and the first chart was from an older thruster, and it was based on what we had in the lab then.
So you're talking 200 micronewtons? Is that what you?
No, just for a thruster. So the thrust here is okay. It's in terms of watts.
You know what? Let's hold this discussion for the design challenge because we're over time on the questions. So good question. And go on to the next talk.
Okay, thank you, Francois.
Thank you.